Just a minute. Just a minute. Doesn't show what I want it to show. Let me see. So this does that. Okay. Can you see my screen of SSA?
Yes, I can.
Okay. All right, folks, let's get started. Just a quick announcement. You must have seen that I have put a third homework, which is to practice the SSA concepts. This is mostly about understanding the use of SSA for copy propagation and then high-level expressions. In the other words, the CAC in the SSA setting. So it will walk you through this, generating some examples and coming up with simple SSA-based algorithms for doing that. So it will be nice exercise. You can take some examples and try to see how things change within SSA. You can even take the same examples which you had for available expressions and so on, and then see how the things become simpler, and some things will not, of course, become simpler. So this is an exercise to look at all these different cases. The second problem is about understanding one use of SSA, which I will be putting up some material about, which is called a sparse conditional constant propagation. But I'm going to quickly walk through that and give you some idea, but then leave you to read that and then understand the topic. So that's what is going to happen. I'll do that on Monday. But you can get started on the first problem, which is about the use of SSA for the two problems that we have already looked at in details, copy propagation and CAC. So that's what is going on. After that, we just have one last homework, which I will give towards the end of the semester. Will be about a couple of weeks as well for that, and that will be on the last topic of the of this syllabus. Mainly, I think some thing related to the dependence tests and the loop transformations, especially parallelization, which are related to those tests. So, and that will be a lightweight homework too, because I don't want to give too much towards the end. So that's why it's becoming a little heavy at this point, I understand. But you have a lot of time to work on different things like project and also the term paper. So please adjust your schedules and try to get things done as per your own pace within these limits. We are giving good bit of time to finish the work, so that's And this particular homework is on the lighter side. It's also just a paper and pencil exercise, only focused on the SSA's applications. If you have any questions about the understanding of the homework or any other stuff, just let me know. You can, of course, come to the office hours. If you cannot, just send it on the Piazza and I'll pick it up there. So with that, let's keep going. So we are going to finish the SSA generation and also hopefully get to the application of SSA, which is dead code elimination. This particular topic of dead code elimination is also covered in the SSA paper that I have put it out there, the original SSA generation paper. So that was the first application they thought of. We will be covering next week a brief introduction to sparse conditional constant propagation, which is SSA based. And then we'll also, in details, we'll talk about global value numbering, which is the real application of SSA, which is also implemented in LLVM. So getting back to our SSA construction, what we saw last time was the first step here, which is being shown, which is about insertions of phi functions. Of course, not at every join, but at the minimal SSA type of construction, which is used, which we had looked at. So using dominance frontiers, we want to insert those phi functions. That is what we had talked about. What we do is first find out the definition point of each of the names, that basic block, and we find its dominance frontier, and we put a gating function with regard to that variable in that particular dominance frontier. We had looked at how to dominance frontiers in a very efficient way, which is order E algorithm, which is typically quite is almost close to n rather than n square. So in practice, this algorithm turns out to be pretty linear in terms of number of basic blocks. The way it does it, the calculation of dominance frontiers, is that it takes it divides it into two steps. One is DF local, which is the local dominance frontier, which means that you go to the successor nodes of the basic block for which we are computing the dominance frontier. And we make sure that those are not dominated by under the definition of dominance frontier, not strictly dominated, to be more precise. And we include those in our local dominance frontiers. Now, there is a propagation step in case a particular node has a region of domination under that particular node. What we do is we take each one of the nodes which are dominated in that region, take their local dominance frontiers, take their union, and we find out if the nodes in those are dominated by the given node or not. And if the given basic block does not dominate it or does not strictly dominate it, then we go ahead and include in the dominance frontier of the immediate dominator node. And so this is a propagation step, and in addition, it will have its own local dominance frontier. We take union of those two, and that becomes the dominance frontier of the given node. So in other words, propagation step means we take the dominance frontier of all the nodes which are computed already. And we take the union and then remove from those the nodes which the current node, basic block whose dominated frontier we are computing, we remove those nodes which are dominated by this given node and keep the rest, and then merge it with the local dominance frontier. And we walk the tree bottom up in this particular case, and that's how we get all the dominance frontiers. And then we take a closure of these, and then there are more computational efficiency step. We stop propagating if we hit a particular basic block where the node is not live, and so on. That way we avoid the growth of SSA in terms of size, and more importantly in terms of time of computation. And then there is a little bit of optimization which is semi-pruned, which is considering this only for the blocks where things are live for 2 or more blocks, and so that we don't have to really, we can exclude all the names which are purely local to blocks. So that's the way the SSA computation is made more efficient. So at the end of this 1A here, we would have generated the dominance frontiers, and here is the thing which kind of details that particular step for us. So we find the names, we list a block, find the list, whatever I just said is shown over here. And we find these phi functions insertion nodes, and using some kind of work list, we try to make sure that we are trying to put these dominance frontiers in the respective blocks. So this now brings us to the second step, which is really important in building SSA, which is how do we populate these phi functions? How do we name the variables overall in the SSA form, starting with our current IR? So this step is pretty nice and intuitive. What we are trying to do here is something which is very, very simple. And let me first just give you a high-level view of the world of what is going on, and then from there we will try and get into the details of this algorithm. So the idea is this, that pretty much we want to walk the IR in the sort of topological order, or in the order of the dominator tree. Now starting with the root going down. We went in the reverse direction earlier for doing the phi function computation, but for this particular step we are going to go top down. And we are going to visit a block here typically. So there might be a native definition point in that particular block of a particular name, like A is defined there. And we want to give it some name, A5, A7, whatever that is. And we are going to keep track of the last name that were given out. Because remember that SSA needs all these names to be unique. So we are going to maintain a counter. And the moment we encounter a new definition point of A, we are going to give out a name indicated by the current counter value, like A5. And then we'll increment this counter. So for A, we'll have a counter which keeps track of its current name that will be assigned from it. Once we assign A5, the next name will be assigned using A6, and so on. So that's how we'll take care of the native names in that particular block. Now, you can see that that particular name becomes the prevalent name in that block. In other words, if some other name would have come into the block earlier, that is getting wiped out by this particular new name, obviously, because it's a redefinition. It's like a kill set. which wipes out all other definitions which are coming in, and this becomes the current definition. So it is exactly following the same logic what we saw in terms of reaching definition. So this new name becomes the prevalent name, and we start all the uses being so all uses of A will be now reassigned as A5. And from there, we will take these steps that the name will remain prevalent in the dominated region of this particular block unless and until it meets another name in a given block, which again redefines it, wipes it out, kills it, and that becomes the prevalent name from there, and so on. And so this process will continue in terms of generating names and pushing them into as prevalent names and so on as we walk down the dominator tree. And so the question is, where does this names last use is in terms of being prevalent? And the answer to that is in the phi function, it becomes a member of. So what happens is, and let me now go and illustrate this process to show you how to go about this using one of our things here. So we'll draw this out for a block, and then we'll walk through the example, the algorithm and the example that is kind of going to make it more clear. So, so as I was mentioning, we are going to enter a block here, and regardless of whatever names we entered with, we would have entered with some kind of a name here. If there was no join here, we would have entered with one name. The other case would be we would have entered with two names if there were a join. So let's kind of for now assume that we don't have any join. We are just coming in with a one edge into the block. And so there must be some name, SSA name, which will be prevalent here. But let's say that we have A inside this block, which we want to rename. So obviously this is a new native birth point, and this is the one which I was talking about as A5. And if there is any use of A in this particular case, obviously this becomes the prevalent name at this point. And that is indicated or that is tracked by a stack. Okay, so at this point we say that A5 is the current name at the top of the stack, and we'll see what are the other names. The other names would be the one which would be coming from into this particular block that would become prevalent and so on. We'll come to those cases. Let's just say that that is A4. In this particular case, A4 was the prevalent. We came into this block, new definition was encountered, that becomes prevalent, and so any use of A here will be written down using A5. How did we come up with A5? Well, our counter was 4 earlier, and for A, and we kept track of that in some other stack, other place, that A's counter is 4, and then we incremented it to 5, and so basically we came up with a new name A5. So all the expressions which involve A in this particular block will be rewritten using this particular name as A5. So in this case, let's go from here 2 blocks, and you can see that this particular block now dominates these 2 blocks. So let's call this as B1. Let's call this as B2 and B3. Now, what is going to happen is, and let's complete this again with a diamond graph that we are always fond of. Okay. Now, in this particular case, what we'll do is we would have completed the writing of all the names in B1. Similar to A, there will be other prevalent names in this particular block which would have come in through this particular edge. Let's just call it at B6. And again, there is no join here, so you can see that that is the name which will come in. Now, in case of B6, obviously there is no redefinition of this particular name inside the block, so it will remain prevalent here as we walk down the dominator tree. And any reference to this B, such as this, will be rewritten to its current prevalent name. So in short, what we're doing is we are keeping track of these prevalent names using a stack mechanism for each one of the names. And here was B6 at the top. It was never rewritten, unlike A, so it remained prevalent, and it does remain prevalent as we go out of this block also, because there was no redefinition of this name encountered. In case of A, however, the prevalent name before coming into B1 was A4, and of course B1 redefined to a new entity, A5, which exists in the region which is dominated over here, unless and until it is, of course, overwritten. And so the new name is pushed off the stack, and it is now the prevalent name and is being used for rewriting all the references to A as you encounter here. Now, what we'll do is, so let's look at the dominator tree over here, which I'm showing. Let's do it here actually. As you can see, B1 dominates here all three blocks, B2, B3, and B4. Okay, so that's what we'll do. We'll walk this down the dominator tree. This is B4, B3, and B2. Okay, all three blocks are dominated. So we can visit them in any order. It doesn't matter. And the algorithm handles this properly. So let us say we go in this particular case to this example. I'm going to rewrite A to another name here. So there's a definition point of A here. And I'm going to put a definition point of B over here. Now, as a result of, as you can see, the phi function generation, this guy will be putting a phi function. The B2 will be putting a phi function in B4 because of phi, because of A. So because this is in the local dominance frontier. So phi of A will be here. Note this fact. And there will be two arguments to it because there are two edges here. And there will be also a phi of B here, which is put in because of B3. Because B3 does not dominate B4, it will be putting. So note that there are phi of A and phi of B in the entrances of B4. So now what we'll do is, let's just do this randomly and find out what is going on with the, let's just do it for this basic block B4 and put a name A over there, another definition of A. So what will happen is now we are going from B1 to B4. Note that. So there are two steps here. There are two things which should be done here. One is we have left-hand sides of these, which are again definition points of A and B. Phi A is generating a new definition of A, and this is generating a new definition of B. As we enter this block, we have three tasks to accomplish. One is we don't know what are the arguments of this phi A, what are the different definitions which should populate this phi A's input. We don't know the same about phi B, okay? And we of course don't know the new names and their propagation further. So what we will do is we will leave the population of phi A and phi B to the respective basic blocks which have inserted those gating functions. And we will not do it here. We will leave it to them. So as you complete the naming within B3, we will use that particular prevalent names, and we will populate that in this phi B. Okay, and the same thing we'll do it from B2 on this side for both A and B. So our job will be to process the L values in this particular case, not R values of these phi functions. That will be left to the predecessors which have put in these phi functions because of their local dominance frontiers. So in short, the name that escapes the local dominance frontier is the one which will populate these phi B and phi A, and that will be done by the rewrite step in the predecessors for which we have the local dominance frontiers. So let's start just processing the L values. In every block, we are just processing the L values first. And at the end of processing of these L values, we will check if there is any step for the local dominance frontiers to populate the phi functions of the successors. So as far as the B4 is concerned, we'll take up this A first. And current value of A is A6, A5. The new name A6 will be generated here. Okay, and will be pushed here at the top. Okay, so that will become the prevalent name at the top of the block. Similarly, B6 was existing, so B7 will be generated at the top of the phi function on the L value side. And as we rewrite this block, we will move from top to bottom, again in the lexical order. We'll take up the prevalent names which are at the top of the stacks. So this will be A6, that will be B7, and they will be used for rewriting all the R value sides. Here, if there is a reference to A on the R value, that will be rewritten to A6. There is a reference to B, that will be written to the B7. And then suddenly we'll encounter the new definition point of A, which is a native definition point in B4. And you can see that we had to reinvent the current name, which is prevalent. And again, by using the same mechanism, A7 will be generated here at the top. This A7 will be the native definition point within B4. And then we will keep going in the B4, and whichever is the definition, whichever is the use of A, we will rewrite that to A7. Okay. B, of course, will remain where it is as B7, and if there is a reference to B, we'll rewrite it as B7 and so on. So in this way, we will populate all the uses using the prevalent names. How will the prevalent names be generated? We will process the L values from the left-hand side. And whatever was the prevalent name currently will be superseded by a new name which we will invent by using current values of the counters. And we'll invent the name by doing A6 current value of the counter, appending it to A. Similar counter, separate counter for B. We'll invent that on the L value side. Be it a native definition or be it a phi function generated definition, for both will follow the same procedure, and we'll populate it. And then once that IR point is populated, we'll move down from there and we'll use the current and prevalent names going down all the way to the end of the block. Now that takes care of the rewrite step within the block itself. What it does not complete, however, is the rewrite step in terms of the phi functions. So the last step that is remaining in processing of each basic block is there a local dominance frontier through which a name has escaped through a phi function? And if that is the case, then I must populate that using the prevalent name which is there currently. So you can see that as far as B4 is concerned, there is no such thing. There's no local dominance frontier. There are no successors, first of all. and there was no phi function in any of the successors. So because of that reason, this last step is nothing is to be done as far as B4 is concerned. So at this particular point, B4's processing is complete. Okay. And what we are going to do is, we are done with B4. We are going to expose the context under which we came into B4 here. So what is that context that was there before? And so therefore we are going back to that particular context. So in other words, all the names which were invented within B4, they no longer exist now. Okay, they're done. We are done with all the names and their uses, such as A6, A7, those were the two, and I believe B7 was another one. So in this example, A6, A7, and B7 were the three names which were generated within this basic block B4, and they were prevalent in there. And if there was further phi functions or anything or any other block which was this wherein this could have been the dominator, they could have persisted there. But there aren't, so we are finished with all the steps here. So at this particular point, they are abolished because they are no longer there, which are to be visited here. Okay, so, we'll get rid of those from the stacks. So we'll cut this A7, we'll cut this A6, we'll cut this B7 out of the stacks, and we will therefore expose the prevalent names which were there before, which is A5 and B6. Those were the prevalent names which will get exposed at the top of the stack. So remember this particular step, okay? So all the names which are locally invented within the basic block, once we complete the processing on that block, and there is no other thing to process from there further. So for example, the tree below this is completely either explored or is not there at all. So in this case, it is a case of the tree being not there at all. All those names will cease to exist in this particular case, and they will be removed from the stack. Now, what we'll do is, and this is basically called as pre-order walk on the dominator stack. That is, once we visit B1 and once next we visit B4, we would have explored the full dominator tree under B4 and completed that and finished the processing of B4, like the way I mentioned, before going back to the place where we came from, which is B1. And that's the pre-order walk on the dominator tree. As you can see, the reason is this, that we enter a particular region, such as B4, and the B4's names are prevalent there, and they will get rewritten as per the local names which will get invented in the dominated region, and then they will populate their phi functions, etc., using whatever names that are invented in that region. And once that region is completely visited, we are done with those sets of names. The ones which will be prevalent will now come from the context from where we came into this B4, which is really B1. So B1's names will again become exposed. Okay, so at this particular point, because B4 did not have any dominator tree below it, we were anyway done, which is a simple case. And we finished all the processing here about all names within B4. We demolished all the L value names which were invented. We got rid of them from as prevalent names from the top of the stack. And now we are ready to visit either one of the B3. So we'll just pick up B2 randomly. Now, as you enter B2, let us look at where I drew this arrow. If there was a use of A here, what should that use be bound to? You can see that that use should be bound to whatever is prevalent there, which is A5. And that is exactly the definition which is coming in here, A5's definition. And if there was a use of A, that will be bound to A5. So that is what the processing will do in the top down, with using the prevalent name. There's no fee function here because there's only one edge, which is a nice and simple thing. We do have another definition point for A, however, in B2. So now what will happen is we'll again put a new name over here. And what will be that new name that will invent on the top of the stack here? Will it be A6 or will it be A7? Or let's say which one was the last one. Will it be A6 or will it be A8? Because these were all invented and done with. So what will be the new name that will get pushed on the top of the stack? So it will be decided by the current value of the counter. Remember, the current value, the counter is monotonically growing. So last time we incremented it from A5 to A6 to A7. So currently it is at A8. So A8 will be the one which will be generated first using the current value of the counter. And that's the one which will be used here and rewritten. So at this particular point, what it means is the prevalent name is A8, which is sitting at the top of the stack, which was generated by using the current value of the counter, which is 8, and of course appended it to A. And from here and pushed on the stack, all the uses of A in this region, the bottom part of B2, will be now wired to or will be rewritten to A8 because that's the prevalent region. And similarly, if there are any uses of B or C or whatever, they will be all rewritten using their prevalent names. So if there was a use of B in this particular case, in B2, as you can imagine, that will be rewritten using B6. Okay, not using the other names which were generated here, like B7 and all that. The reason is obviously those names were prevalent in the region dominated by this bottom block B4, but they were not at all prevalent. What is really prevalent is B6 has come in here because of the region dominated by the birth point of B6 and has remained here. Particular basic block B1. It is again, there was no redefinition of that name, and because there was no fee function and there was no native birth point, so that remained where it is, and therefore the prevalent name remained at B6. Okay. So this B6 was the one which will be used for rewriting everything here. Remember that. And now one thing that we had to really do is, in this particular case, the last thing that we had to do is we had to find out if there is any local dominance frontier which involves B2. In other words, we had to find out B2 successors, to be very, very simple, and find out which ones of those have fee functions in them. And if they have a fee function in them, then we had to populate those using the current prevalent names. So the successor of B2 in this case is B4, the block down. And it does have phi of A, it does have phi of B. Both of them are there. So they will get populated. Phi of A will get populated using the prevalent name, which will be A8. A8 will be a part of this. And phi of B will get populated using the current prevalent function, which will be B6. So these two will get populated, A8 on the left and right it, just for be more clear, A8 here and B6 over there. Okay, so these two will populate respective fee functions. And how did we decide on that? So once we finished the complete processing within a basic block, what we did at the last step is looked at the successor of the current block and see if there are any fee functions. What does that really mean? Is if there is any local dominance frontier, which means the block which I do not dominate, which is my successor, through which any name has escaped, and which basically means that I must populate the fee function by using my current name, because that will be the name which will be escaping into that dominance frontier. And we simply did this simply. At the end of processing of the basic block, we looked at its successors, checked the phi functions, then use currently prevalent names in my current block, and then I just populated all those phi functions using those. Now, so that completes now the processing of B2. And once we complete processing of B2, we do the same thing. We abolish all the names that are generated within B2 and expose the previous names through which we entered the B2. Again, because we are back in the region of domination of B1. If we had some nodes dominated by B2, of course, visited all of those here and finished those and their processing by using B2's names as the prevalent names in those regions. But there weren't none. There is no node which B2 dominates, just like B4 doesn't dominate any node. B2 also doesn't dominate any node. And so the processing of B2 is over at this particular point. When we go back, we'll abolish all the names invented within B2. And one such name will be A8, as you see here. So that will go away, which was sitting at the top of the stack. A8 was sitting. That is gone away. And again, A5 is exposed from there. Now we are going to go to B3. There again, we'll use the prevalent names. So what are the prevalent names? A5 at the top of this, A5 is be there. And B6 is there. And we'll do again similarly processing from top to bottom, which is using the lexical order. We'll rewrite the R values there. We would then come to B's definition point, and B6 was there. So last time the counter value was at B7. So we'll invent B8 here. And push that at the top of the stack. We'll rewrite all the uses of B using B8. And finally, after the B3's processing is over, we are going to look at its successor to check if there are any fields in there which we must populate. The successor of B3 is B4, the bottom block here again. And that has a phi function on B, which is shown here. So this will be if B's function, phi of B, and one of the arguments there will be one argument of B, which came from this side, left-hand side, which was B6, I think. Correct me if I'm making any mistakes, which was sort of rewritten by this particular B2 into these things. B6 was rewritten, and the other one will be written by B3 using its prevalent name, and that will be B8. And they will be populated like this as the last step of processing of B3. I'll find out which is the name which is prevalent, and take that and go to the respective gating function, which is in my successor, and populate it there. So as far as B is concerned, B6, B8 take care of that. And as far as A is concerned, again, we had on the left-hand side A8. So this is a phi function of A8 coming from left-hand side. And what are the prevalent name over here? That I believe was A5. Because A5 was generated here, that remained prevalent here, went all the way through B3, there was no change in it, and that came all the way down, so this is A5. And that takes care of all this, and that means we are done with the processing of B3 here. We again go back We have finished at this particular point completely the subtree, denominator subtree below B1. And of course, the whole processing of B1 itself is done too. And at this particular point, we are ready to go back to a place where we came into B1. And so from here, when we go back here, again, whatever names were introduced in B1, what was that? A5 will again be destroyed. And what will be exposed is A4. And B6 anyways is prevalent. So it wasn't originating in B1. So it will remain where it is. Whatever were newly defined names in B1, they will be the ones which will be destroyed, which is A5. So when we go back to the dominator tree, from where we came into B1, we will see the original names, A4 and B6, and we'll start using those again. And the whole process will repeat as we go through the same region of dominance and so on. So the key steps which are involved here is, let's go back to the previous algorithm. And before we do that, are there any questions about this overall method? What we are doing is, let me just quickly recap the method. We are walking the dominator tree from top down, from root to the leaf nodes. At each point when we process the corresponding the basic block, we first go to the root block of dominator tree. We will rewrite the names in that block through phi functions. If there are any phi functions there, we'll only deal with the L values of those by inventing new names. Or if there are any new definition points, again, we'll deal with those by inventing new names. How do we do that? We take the current value of the counter, append it to the variable which we want to rename, and that becomes a new name. And that name is pushed on the top of the stack as a prevalent name. We would generate such names, native or phi function originated L values. And we will do the lexical ordering. We'll walk from top to bottom, and whatever R values are there, we'll rewrite them to the respective generated names in that block for prevalent names. And at the end of this processing of the block, all the uses, all the definitions in that block would have been covered. So the last thing that we will do is we'll find out the successor of this block. And if there are any phi functions there, they will be populated using the prevalent names in the current block. That would mean that we are populating the dominance frontier of local dominance frontier of the current names which are prevalent, which is what we should be doing. And at this particular point, everything is done with the block. If there is no further subtree below it, we will go back. If there is any subtree below it, we'll follow this particular procedure randomly by taking any block that is dominated by this current block, which I'm finishing. Now at this point, we'll be done with the complete dominator tree below a given block. We'll destroy all the locally invented names in those blocks and expose the top of the stack to the originally prevalent names. And we'll keep doing this and repeat this process by populating the names everywhere, and by making sure that the R values are again rewritten to the prevalent names which were there in the dominated regions. So that's the process, and that is exactly what is shown through example and the algorithm. So let me clear this up and go back Let me see if you have any questions at this point. But any part of this which is not really understood, it'll take 1 minute, and then if not, then I'll go back to the formal algorithm, and then we'll just quickly do some example, and that will clarify how this process works. It's a very clean and very nice algorithm, wherein it is sending the values in terms of which value becomes prevalent where. So, are there any questions? Okay. Is there any questions, Nathan? No?
There's not anything on chat.
Okay. So now let us look at this formal algorithm that I was mentioning, which is exactly doing this. It will be very easy to understand this now. So basically pre-order walk, as I was mentioning, and one stack for global name, which to show which is the prevalent one at the top of the stack. And we have different counters for different names. And then starting with the root block, what we'll do is we'll walk in the pre-order manner in the dominator tree. Generate unique names on the L-value side for each fee functions, and those become prevalent, so we'll push them on stacks. Take each of the operations in the block, rewrite the uses with the current version from the stacks. That should be easy because it's the top of the stack. And then rewrite the definitions by generating new names and pushing them on the top of the stack using the current value of counters. And then the last step, which is C here, you can see it's very clean and neat, is this dominance frontier, which has local dominance frontier, which has escaped, and which fills in the fee function by the current prevalent names, the parameters of fee function. This is a local dominance frontier, which I have been talking about. And immediately successors block, you can see that if there's a fee functions placed there, then it must be a local dominance frontier which has placed it, and the name which is prevalent there will be the one which will be used for rewrite step. So that's what is done in step C. And recurse on B's children in the dominator tree. So once we are done with this, all this processing, steps A, B, C are pertinent to block B. And once we're done with this block B, then go to B's children in the dominator tree. So maybe B is dominating some other nodes. And so we'll do this processing for each one of them. And once we are done, in step D, which is what is called as on exit from block B, and the complete dominated region from there below it, we're done with processing of B completely at this point. When we are done with the complete subtree below it. And once you are done with the complete subtree below B, then you can pop off all the names which were generated in B. And whatever names were exposed, those are the ones before you came into B are the ones which are exposed, and then the process repeats further from there. So this is the algorithm. And we have done all this, so I'm not going to worry about this. So this is the example. I'm going to just quickly show you a few steps, and then because we have gone through it in such details, I don't believe we have any. I will rest the rest of the example. I'll let you go through it. um, so you can see there are all kinds of fee functions here populated for A, B, C, D, whatever in different blocks. So minimal SSA and step 1 here. Step 2 is where we had to kind of invent the new names and then populate this. So that is what we had to do this second step here. So this is that again the algorithm, and here was the more detailed algorithms for each. For each name, we have global, counter for that name, counter of I. So there are several names here. Each one of them has a counter value initialized to 0 and a stack which is null. Okay, so that's the initialization step. Then what we do is we have one other step here, which is just generating a new name. How do we do it? For a given V, some name, we want to generate a new name. So we look at its counter and we increment it, and then we append this counter to the name, and that's the current prevalent name, and we push it on the top of the stack, and that's basically it. Okay. So that should be fairly clear, the left hand side steps. And then the rest of them is just this basic block business, the new names, and then we basically do all these things, push that, generate a new name and push it on top of the stack, and then use the operation lexicographically down going. We just rewrite it to that name. And if there is a new name, such as an X, we'll generate that, and that will become the prevalent name. And then in the next step is to write the appropriate fee function parameter in the successor, and then that will do it in the third step. And so each of the successors, we will then visit them using rename of S. And once we are done with the substate here, we will destroy all the newly generated names in that B, such as all the names which were on the L value side on top of those stacks. They will get rid of those and expose the old ones. And this process will be going on and on and on. So I suggest you go through this. Here is where we start. These are the counters of these examples, and assume that, of course, A, B, C, D, they're saying that they were defined before we came into some B0 block. So they had some originating definitions, and we are going to try and do it in terms of these names, which are prevalent. And I0 was, there's no definition for I there, so that's why this counter is 0. Obviously, as we entered this B0, we use the current name using the current counter value 0, I0. I pushed it at the top of the stack, as you can see now. That becomes a prevalent name, and we rewrote this I to I0 as a new name. We finished. There was nothing else about B0, so we went, and now we had to just rewrite the successors using the prevalent names. So the successor of B0 is B1, basic block B1, as you can see. And we do have several phi functions there, one for each A, B, C, D, and also I. And so this is the local dominance frontier through which names are escaping. And whatever are the prevalent names there in B are the ones which we are going to put it in the B1 for rewriting purposes. So B1 contains, for example, what you call it, the phi functions, and with regard to each one of these A, B, C, Ds, and Is, and they are rewritten as you can see: A0, B0, C0, D0, I0. These are all prevalent names within B0, which are used for populating those. Okay, and of course, the second populating function, which we have, our second one, will get populated with the back edge, but those names are not known yet. And so whenever we process B7 in this case, which is our back edge block, and then we do its successor, that is the point at which these names will be known for those A's, and that will be used for populating B1. So the rest of the example I'm going to skip because I think it's fairly intuitive and clear, but do step through it. And if we have a choice of whichever way we can visit the dominator tree. Different orders of traversal will generate different kinds of SSA-IRs, because the phi functions and all will get populated by different names. But they're all legal. Each one of them is legal because it preserves the condition for SSA. They have unique names and they are populated properly at the phi functions. Those are the conditions. There is no strict prescription that you have to generate the SSR only in this particular way, that you have a prescription on traversing the blocks dominated by in the given dominator tree. You have only one order to process it. It's not true. You have any pre-order which is correct. That's what these algorithms say, and that's why if somebody picks to go to B2 instead of B3 in this example, whereas somebody decided to go in some other order after visiting B1, obviously it will lead to different types of SSA IRs, which will be different, but they will all be correct. Any questions about the SSA generation? We talked about semi-pruned and pruned in terms of the SSA generation, and I won't get into that now. Any questions about SSA generation? Okay. So this SSA is really, as you can see, is before we complete the topic of SSA construction, I want to mention one important step, which is about deconstruction. So the SSA is generated after, as you know, the triples or quads are generated. The SSA is generated by this particular algorithm. It's populated. And then the SSA is used for doing all optimizations, such as data flow optimizations, PRE and whatnot, all kinds of different available expressions, global value numbering, all these different optimizations are done using SSA, which is an abstract IR, which is clearly showing which definitions are lumped together: constant propagation, copy propagation, all these things is very, very fast and unified using SSA It is the IR which is used to reduce the analysis time and optimization time mainly. We are going to look at some optimizations, as I said, and how and why SSA in fact is extremely fast in terms of doing those. We'll look at those also. But then after all these optimizations are done, we are going to give this SSA IR and lower it to a non-SSA IR, which is like our original code. And that is the one which is triples or quads, which is being used for register allocation and so on. So how is SSA to be interpreted there, and what is really done in deconstruction? So it is just an implementation of this phi function, which is inserted here. As you can see here on the right hand, simple example, we have phi of x17 is equal to phi of x16 and x11. What is really happening here is one of the things is coming from left hand side, x10 is coming from left hand side edge, x11 is coming from right hand side edge. And so we really, what we are saying is we are inserting the copies in terms of implementation of phi function. X10 is assigned to x17 and x11 is assigned to x17 over there, and then x17 is used further from there. So when SSA is deconstructed, we insert a lot of copies like this to implement SSA's intent. And then we give it to the register allocation and whatever other phases that follow, which will really implement this interpretation. So now if we get different registers, one for X10 and another for X17, for example, it is going to lead to a lot of register copies, and that doesn't make sense in the code. There is another efficiency issues of doing these register to register copies. There are techniques like coalescing, which means merging these nodes into one and considering them a unified range as against a split range with copies, and that allows you to get rid of these copies, and that's something which we'll see when we talk about register allocation. So that is SSA deconstruction. Now, before we end today, using maybe last 5 minutes or so, I'll introduce this as an optimization, which is a very simple and straightforward optimization based on this SSA technique. And in a sense, I will talk about why SSA here. So this optimization, it's called as dead code elimination, which is a very powerful optimization to get rid of what is useless in the code. So here is the deal. So let's imagine a function here with a certain output value, which is being sent as a return value. And this function, like most programmers do these days and also in past, was generated by using a lot of cut paste operations. And a lot of operations just remained in this function, which were not really useful to the computation of the final result of the function. So the idea here is start with the final or useful result of this function, operation of the function, and then move backwards and see which are the other operations in the IR really contributing to this execution of this function, or which are essential to the data and control flow, which is necessary to compute the final output of the function or useful output of these functions. And if there are instructions there or operations there not really useful, don't mark them. Mark only the ones which are useful, and do this marking using SSA edges, and that's where the efficiency comes into picture. Whatever is left unmarked, get rid of it. It is as simple as that. So you can see that we pretty much had to trace the backward data flow from the useful or critical operation of the function all the way to the beginning, and it will be very expensive to trace it through all kinds of analysis followed by these things, reaching definitions and all these things. And SSA introduces a very simple and very clean and very quick way to do this. So what are the critical operations? Typically, as I said, return values are one important thing, or the IO statements, because they are putting out values on your screen or whatever. So they must be important. Linkage code, because that allows you to call other functions and so on. Maybe device drivers also. So that is important. And other calls to other functions, because the interprocedural flow otherwise will be jeopardized. So these are what is typically called as critical operations, or operations that are a must for the function to operate correctly. And by starting with these critical operations, we'll do SSA based marking, and we'll try to get rid of the ones which are not really needed. So here is an example of, I won't get into that details now, but we'll just touch bases on this, and next time we'll get into this. So as you see here on the right hand side, we have a control flow graph of a particular function, and this particular function is returning some value C2, which is critical. So our goal is, given all this representation, mark all the values which are important for computing C2, get rid of everything which are not important, and in order to do so, we will have to be very, very efficient. Potentially, we may have to visit each statement multiple times and so on, and it might slow us down. So how to do this very efficiently is basically the goal. Now, how do we do it? This is called as the SSA chain of the values and their use and so on. So SSA allows you to build this chain, and what we'll do here is for C2, we will find out where this SSA value is originating. Now that is very simple, because each one of these names have a unique definition point. Unlike the previous IR, wherein there will be 5 different places for C, let's say. Okay, in this particular case, there are probably 2 or 3, but in general, there could be many, many ones. And which is the one which is really coming in here, which is the definition which is coming in here, is very unclear. And even then, amongst those, to find out which is the rich definition wherein I should go and mark, that will be costing another piece of work here, there. So here what we'll do is, when we say return C2, we'll take the SSA name C2, and we'll find out the SSA edge which binds this to the definition of SSA definition that reaches here, which is only unique, because there has to be exactly one definition. There cannot be multiple C2s present, and we'll trace it. So we'll go to 12. We'll say that, hey, 12 is really now to have 12, we'll look at the phi function there, which is in the 12, and we'll say that we must have C1s and C3 here, because without those, I really cannot construct C2 properly. Now I'll go and mark C1 and C2. C1, let us say where it takes us. C3 takes us to number 15. and C1, I believe, takes us all the way in the beginning. So at this particular point, we have C1's path is finalized. We need just C1 from there, and we don't need to do anything further on C1, but we'll need so far 17, 12, and 15 in terms of the definitions. Now look at 15. 15 needs, in other words, C2 and Y, which is the right-hand side variables. C2 is again 12, so that is needed, that we are already marked because C2 is needed, of course, at the 17 side. But Y is yet another one, so we'll trace where Y is. Now, as far as Y is concerned, we have only one definition here, which is number 2. We'll mark that. And we'll continue this particular process over and over again and keep marking more and more. And in that particular way, we would have marked all the definitions which are needed for computing C2. Now there is one other element to it, which I'll just mention, which you see here. And that's another element which we'll look at in more careful details next time. But apart from these data flow branches, operations like 12, 13, 15, etc., we want to find out, can we get rid of here some branch predicates because they may not be needed. And for that matter, we'll use a very interesting concept which is called as a reverse dominance frontier of a particular operation. Here is a key idea which I will just mention. So a branch predicate, whichever way it goes, is irrelevant. For example, if when it comes to certain blocks, you can see that in this case, number 4, whichever way this executes, x equal to 0, we'll take different types of branches. Maybe one will go through 5, second will go to 6, 7, whatever, 9, 10, and come at the join point. But as far as this block, big block is concerned, which starts with 11 and ends with 14, execution of that is not really affected by the outcome of x equal to 0. So in other words, when it comes to post dominator, all the intervening branches have 0 effect. And so we might as well remove them as far as the post dominator is concerned. If there is some other control flow which is needed for intervening execution, that's different. But as far as the block 11 to 14 is concerned, the branch x equal to 0 is not relevant, and we could get rid of it. And that is the principle that is used by this dead code elimination algorithm as the second guiding principle. So once we note which are the critical operations which are needed for this data flow of this C2, we find out that the block surrounding that operation, does it need a particular branch or it doesn't need? If it doesn't need, we'll get rid of it. So only the branches which are needed for the proper execution of marked data flow operations will be preserved, and those are the ones which will be preserved are not the ones for which this particular block is a post dominator. And we'll do this analysis and we'll keep only those branches which are necessary. So in other words, if none of the operations 5, 6, 7, 8, 9, 10 were marked, we will obviously not have any particular reason to keep certain branches like the branch at 4 because that control can come whichever way. The operations will be all deleted anyway. The control will come whichever way, and if operation at 11 is useful, it will land there anyway. So that's the principle which will be used to keep certain branches, get rid of certain others. So if an underlying data flow is not necessarily the surrounding control flow to that is also irrelevant because it's not marked. And then as far as the post dominator is concerned of a given branch, the post dominator executes just fine without the branch predicate itself. Like it doesn't matter if we remove x is equal to 0 and put some other predicate there, the control will eventually anyway come to 11. So that branch becomes irrelevant there, and that's the way we find out if certain predicates are essential or certain are not, and the ones which are not are removed. And once we remove these useless data flow operations and useless control predicates, we can do certain restructuring, and that will lead to what is called as a dead code removal. So what exactly is dead code removal? It is the removal of necessary control flow and necessary underlying data flow, or rather unnecessary control flow and unnecessary data flow, which will still preserve the semantics and which will still guide the execution to generate the correct result with the critical operation. That's what the minimal such data and control flow to be preserved is basically dead code elimination. And why SSA? Because it allows you to go back and forth very quickly using these SSA edges of essentially finding the definition point of a current use and trying to trace it based on what we call as SSA edges, and that's the reason. So let's stop here. Thank you, and we'll have office hours now.